Right, so here example 12 for proofs. First, we need to prove that x squared is congruent to 1 mod 8 for all odd numbers x, or I would just emphasize this to all odd integers x. And then for part B, we need to prove that the last digit of 7 to the power of 2021 is 1. Let's just prove part A first. Now recall that an odd number is expressible as 2 times a certain integer plus 1. Let's just substitute this for the value of x to our congruence right here. So notice that x squared is equal to 2k plus 1 for some integer k. We can expand this into 4 times k squared plus 4k plus 1. Now we wish to show that this is congruent to 1 modulo 8. We can subtract 1 from both sides to get 4k squared plus 4k is congruent to 0 mod 8. Now notice here we can factor both things by 4k. Now we're left with the inside being k plus 1. Now notice that we already have a factor of 4 right here. Therefore, we wish to show that this expression here is congruent to 0 modulo 2. Or in other words, this has a factor of 2. Now since k could be any integer, we can set k to be either odd or even. So if k is odd, therefore this thing is even. And since an even number has a factor of 2, this case will be done. Similarly, if k is even, well, we're already done anyways because k has a factor of 2. And that covers all the cases, and we have proven that this is congruent to 0 modulo 8. And hence, this case has been proven. Now another way to realize this is that the product of two consecutive integers, notice that k and k plus 1 are consecutive integers, will always be even. So therefore, this expression has a factor of 4 times 2 or 8. Next, we wish to show that the last digit of 7 to the power of 2021 is 1. Now for this, let's just observe some small values for our power right here, or index right here. So I just observe 7 to the first power. The last digit will be 7. What about 7 squared? 7 squared is 49 and has a last digit of 9. 7 cubed is 343 and it has a last digit of 3. Likewise, 74 has a last digit of 1. Now, if you notice that this cycle repeating in the cycle 7931, 7931, and so on. Now, here we wish to prove that this sequence or this cyclic sequence is maintained for all larger values of these indices, as those indices grows greater and greater towards the positive integers. Or in other words, in a more general case, or I would just write it here, we wish to show that 7 to the n is congruent to the 4 possible cases. It can be congruent to 7, 9, 3, or 1 if our index right here, n, is congruent to 1, 2, 3, and 0 modulo 4, all respectively. And we're looking here modulo 4 since our cycle of the last digit of 7 to the power of something repeats every 4 times. So let me just finish write this thing right here. So we wish to prove that each of these cases is true. First, let's just prove the first case, which is when n is congruent to 1 mod 4. Notice that we can rewrite n as 4 times a certain number, let's just say a1 plus 1. Let's just plug it in to our equation or expression, I would say. So we have 7 to the power of 4a1 plus 1, and we should show that this is congruent to 7 modulo 10, since everything modulo 10 will be the last digit of that number. And although I forgot to write this on the end, so working this at modulo 10. So here with the rule of indices, we can rewrite this into separate powers. So 7 times 4 to the a plus 1 times 7. Now notice that we can kind of like separate the powers right here and just calculate 7 to the 4 separately. Now to do that, we can just calculate 7 squared first, and then after that we can reduce it modulo 10, and then we can square it again and then reduce it modulo 10 and then multiply it by 7. Alright, so let's see what we have. So it's 7 squared, and don't forget the a1 times 7. 7 squared is 49, and when reduced modulo 10 is 9. So hence we have 9 times 2a1 times 7. Again, we can separate this again. So we have 9 squared, which is 81. When reduced mod 10 leaves a value of 1 to the a1 times 7. And we know that 1 to the power of any integer is just 1 itself, and therefore we have proven that this is congruent to 7 modulo 10. Alright, I'm going to prove that n is congruent to 2 modulo 4 case, and I'll leave the rest as homework because those proofs are very similar to the first two of them. So notice that for n is congruent to 2 modulo 4, we can rewrite this as n is equal to 4 a2 in this case, let me just suppose that, plus 2. We can substitute n with this generalized value. So I have 7 to the 4 a2 plus 2. Again, we can rewrite this with the property of indices, and let's just as well separate the powers right here. Notice that 7 squared is 49. When reduced modulo 10 is 9. So 9 squared a1 times 49. Or might as well reduce this modulo 9, so this will be 9. So 9 to the power of 2 is, well, 81. When reduced modulo 1 is 1. But raised to the a1, where a1 is, it's a2. Again, a2 could be any integer, so 1 raised to any integer is just 1. So this expression is congruent to 1 modulo 10, and therefore we're left with a 9 right here. So therefore this whole expression will be congruent to 9 modulo 10. Now again, like I said, I'll just leave the other cases to let you guys prove that on your own, since they are pretty similar like the others. And once you've proven this identity, we can go back to our question to see our index right here. Notice that 2021 is 1 more than a multiple of 4, or in other words, is congruent to 1 modulo 4. And based on our generalized cases, the last digit right here will be 7. And this ends this video pretty nicely.